Recording is on.
So, thank you. Welcome everyone to the Spectral Geometry and the Clouds. This is the first talk of the year, so Happy New Year, everyone. Today we have the pleasure to have Nikolay Filonov from St. Petersburg University, who will speak about the Polya conjecture for Euclidean balls. The stage is yours.
Thank you very much. And once again, Happy New Year to everybody. And thank you to organizers for the opportunity to give a talk here. I would like to tell something about the Polya conjecture for Euclidean balls. And this is joint work with Michael Levitin, Joseph Polterovich, and David Sher. And let me say something what about is it. Take a domain omega, bounded domain in Euclidean space with Lipschitz boundary, and we consider two very classical problems in omega, which are written here. We have the Laplace operator and either Dirichlet boundary condition on the boundary or a Neumann boundary condition on the boundary. We have two discrete spectrum for Laplace Dirichlet and for Laplace Neumann, and we introduce the counting function of this spectrum, which we denote by n with index d. This is the number of eigenvalues for Dirichlet Laplace which are not greater than lambda n, and with I'm sorry for this notation, subscript n. This is the number of Neumann eigenvalues which are not greater than lambda. Lambda is the spectral parameter, of course. And the Polya conjecture, it was formulated in the very popular book Mathematics and Plausible Reasoning by Polya in 1954. He conjectured that there are uniform bounds for these counting functions. The counting function for Dirichlet is always less or equal than some constant times lambda to power d half, and counting function for Neumann eigenvalues is always greater or equal to the same quantity. The coefficient here is explicit. It's the volume of unit ball times volume of the domain itself over 2 pi to power d. And this is just the coefficient in the Weyl law for the asymptotics of eigenvalues. It's known that for, say, for Dirichlet problem, that for all bounded domains, we have the asymptotics, these counting functions, the behavior of these counting functions in principle, well, principal term of the counting function when lambda goes to infinity is just this function. So if the conjecture is true, then this constant is sharp. It cannot be optimized because at infinity it's just equality. And later in 1961, Polya himself proved this conjecture for tiling domains for Dirichlet problem, and Kellner in 1966 proved it for tiling domains for the Neumann case. The domain calls tiling if the whole space RD can be covered by copies of this domain without intersection up to measure 0. So let me show some examples like this or like this. This lizard is a tiling domain for the plane, or if you want like this. This rider is also the tiling domain. And so we have some arguments in favor of Polya conjecture. First, we have that it's true for tiling domains. Next, it's next there is Weyl law, which is to term asymptotics for the counting functions. It's not proved for all domains, but many people believe that it's true. And in this two-term case, we have that for Dirichlet case, the counting function behaves like, this constant CW is the constant in Weyl asymptotic, so it's just this ratio volume of unit ball times volume of the omega over 2 pi to power d. This the same coefficient times lambda to power d half minus for Dirichlet case plus for Neumann case another explicit constant times next power of lambda to power d minus 1 half. And so if this is true, then for such domain the Polya conjecture is also valid, at least for large values of spectral parameter lambda. The next argument is that, it's for the large lambda. What about, is it possible in general to have some uniform estimate for all lambda and for all domains? And it turns out that yes, it's possible. And in 1983, Lee and Yao proved the following estimate, which is really valid for all bounded set omega and positive spectral parameter lambda. The counting function is lesser or equal to the following quantity, which is just principal term of Weyl asymptotics times some extra factor d plus 2 over d, everything to power d half, which is of course greater than 1, but nevertheless it shows that uniform estimates do exist. And in 1992 Kruger proved a similar estimate for the Neumann counting function, estimate from below. Once again, it's the principal term of Weyl asymptotics times this fraction 2 over d plus 2, which is of course lesser than 1. And the last argument, which for me personally is the strongest one, is that until now there are no counterexample for Polya conjecture. Even with modern computers technology, there are no counterexamples. So it's this conjecture is it's very probable that it's true, but for more than 60 years, it was the answer was not known even for the disk in the plane. And now we managed to do it. So let me formulate our results. Let me start from two-dimensional case. In 2D case, here the volume of the unit ball is just the area of the disk, it's pi, and the Weyl constant is the product of volume of unit disk times once again volume of unit disk. Now we consider the first result is for the disk in the plane. So this omega is also a unit disk, and so we have 1 over 4. And we can prove the Polya conjecture for the disk, that counting function for the Dirichlet eigenvalues is lesser than lambda over 4, and counting function for the Neumann eigenvalues is greater than lambda over 4 for all positive lambda. The next case which we are able to consider is the sector in the plane, secular sector in the plane. If we fix an angle alpha between 0 and 2 pi and consider the following set in the plane, here r and pi are polar coordinates, then it's clear that the area of such sector is equal alpha over 2. The Weyl coefficients now is alpha over 8 pi. And once again, we can prove the Polya conjecture for the sectors of the disk. For all alpha between 0 and 2 pi, and for all spectral parameter lambda, we have that the counting function for the Dirichlet eigenvalues is lesser than alpha lambda over 8 pi, and counting function for the Neumann eigenvalues is greater than this quantity. And the next result is multidimensional. But in multidimensional situation, we can deal for the moment only with Dirichlet case. Once again, we consider the ball in RD. The volume of unit ball is known to be equal to this number, pi to power d half over gamma function at this d plus 2 over 2. And so Weyl constant also can be written explicitly. And our main result is that for ball in Euclidean space, for all positive lambda, we have also this inequality, that for Dirichlet case, the counting function is less than lambda to power d half over this numbers 2 to power d gamma of d plus 2 over 2 squared. Well, so it's the probably the first result for domains which are not tiling, where we can prove the Polya conjecture. Well, and now let me say some several words about the proof. And we start from the I will speak mostly or maybe only on the Dirichlet case. It's more simple. And we start with the two-dimensional case. If we consider the disk in the plane, then we have the separating of variables. And we use, of course, polar coordinates once again, and eigenfunctions of the Laplace operator for the Dirichlet problem in the disk are written explicitly in terms of Bessel functions. It's the product of this exponential, which is very simple, I m phi. Phi is angular variable. M is arbitrary integer number. And this exponential multiplied by some function of radius. Here G with subscript nu is the Bessel function. And our argument is this number G little times R. R is the radius of the point. And G with subscript nu and k is the case 0 of the Bessel function J nu. It's well known that all zeros of Bessel function are non-negative, and we can enumerate them. And in this situation, the eigenvalues are equal to these numbers, to these zeros of Bessel functions squared. And therefore, we can write explicit formula for the counting function of eigenvalues for the value of this counting function nd at point lambda. We have to calculate the zeros of Bessel functions. It's first, it's the number of zeros of Bessel function J naught, which are not greater than square root of lambda, plus twice the same quantities for the function Jm. Well, we have here exponential e to power I m phi, and m is integer number. And when m is 0, then we have these zeros of Bessel roots of Bessel functions once, and for m positive we have these zeros twice, for m and for minus m. So it explains why I take this sum twice. So we have to understand something about the roots of Bessel functions and the distribution of roots of Bessel functions. And our co-author, David Sher, proved the following explicit and uniform, which is important for us, that this bound is uniform in the number nu of Bessel functions. The number of zeros of Bessel function J nu, which are less or equal than square root of lambda, is not greater than the following quantity. It's for the first time this function probably seems rather complicated, but it's very important that it's an explicit function for which we can understand its property. So it's square root of lambda minus nu squared minus nu times arc cosine of nu over square root of lambda, everything divided by pi, next plus 1 over 4, and integer part of all of this. Of course, integer part, because the left hand side is always integer number, so we can here also write integer part. And here I would like to say that it's, at least for me, it's very impressive and very astonishing that it's possible to write down some explicit new formula for estimating of zero of Bessel function. Something new for a Bessel function in 21st century. It's I would say very cool. Well, so next we use only this. We use this bound, and next we use only the properties of this function. So let me consider this function more accurately. So we fixed now spectral parameter lambda positive, and denote this function by g capital. G capital of t is this function 1 over pi times square root of lambda minus t squared minus t arc cosine of t over square root of lambda. This function is defined on the interval from 0 to square root of lambda. And it's clear that when t equal to 0, then it's simply g of naught is g of 0 is square root of lambda over pi. And g at the right end of this interval, g of square root of lambda, here we have 0. And when t equal to square root of lambda, we have arc cosine of 1, so it's also 0. So at the right end, it's 0. Next, we can calculate the derivative. It's minus 1 over pi arc cosine of the same thing, t over square root of lambda. And so we see that this first derivative is always negative. So g is a decreasing function. And next, we also can calculate the value of first derivative at the ends of this interval, and g prime of naught is equal minus 1/2, and g prime of square root of lambda is just 0. And finally, the second derivative turns out to be always positive. So G is this function G is a non-negative, strictly decreasing convex function. So I'm sorry. I would like to draw something. Can you see what I draw now?
Yes, perfectly.
Okay. So it's very. I'm sorry, it's very rough, but very rough. It's the graph of this function J, and it's a decreasing convex function, and we want to understand something for this function, or maybe I would like to say for such functions. We would like to understand something about the sum of what? For this function, we take the value as the integer point m. Next, we add 1/4 and take integer part of this stuff. So we have to calculate this. We have to prove this inequality that for each integer point m, we take g of m plus 1/4. We take integer part, and we sum these quantities for m from 1 to up to square root of lambda, and for 0 we take 1/2, because I repeat in the in this expression for counting function, the number 0, the roots of Bessel function J naught we take once, and the roots for J with natural indexes m we take twice. This why I write here 1/2 of G naught plus 1/4, and here the rest of the sum without this 1/2, and everything must be less than lambda over 8. Of course, the area under the curve, this area, can be also the integral can be calculated immediately, and it's just equal to the quantity which it must be equal, lambda over 8. And so we have to prove such inequality. It's something about the counting of integer point under the curve, and the curve depends on a large parameter, and we calculate some integer point here. I'm sorry, it's not visible, I guess. Well, it must be integer point somewhere here, and it's this issue is well developed in the analytic number theory. There are very strong methods to obtain the asymptotics of such things when the parameter, in our case parameter lambda, goes to infinity. But we and of course the main term of such asymptotics is always the area under the curve. So in our case lambda over 8. But we don't need the asymptotics. We need the estimate, uniform estimate for all values of lambda. It's another story, and so we don't use the number theory methods, and we instead of it we use the specific properties of this function g. So we prove the following theorem. Assume that we have a function, now I denoted by little g, which is defined on the interval AB, A and B be integer numbers, and we assume that it's non-negative, decreasing convex function. Here all our properties, it's non-negative, decreasing, and convex. And moreover, assume that the derivative of this function is always between -1/2 and 0. I recall that it's just our situation our function g, the maximal value of absolute value of its derivative is 1/2. And assume that this derivative is always in this interval, and assume also that the last value g of b is equal to 0. Then we have this inequality. For arbitrary function g satisfying this 1, 2, 3, 4, 5 assumptions. And it's clear also that this theorem, this bound, together with theorem 4, which I recall this is it's the David Sher's bound for a number of zeros of Bessel function. Together, these two facts imply the Polya conjecture for the Dirichlet problem in the disk. Now let me try to explain why this theorem 5 is believable, why one can believe that it's true. First, let me say that if we take, let me once again draw something. If we take 2 points, m and m plus 1, and we consider this the half sum of the value of our function, g of m plus g of f plus 1/2, then it's exactly the area of the trapezoid here, and the integral is the area under the curve. So it's I hope that it can be seen from this wonderful picture that these numbers are very close to each other. And so if we now we summarize over all m from a to b, and we then obtain this sum g of a over 2 plus the sum over m, the values g of m from a plus 1 up to b. What right to at the end point b, it doesn't matter because we assumed that g of b is 0. And so it doesn't matter if we write g of b over 2 or g of b, or if we don't write it at all. But I want to say that this sum in very rough, in this very rough picture, this sum must be approximately equal to the integral. And we want the inequality. On the other, the next point is that we have in our sum this theoretical number function, which is an integer part. And if you take a random number x, then its integer part is a number which is between x minus 1 and x. And so in average, it's if we don't know, if we know nothing about the number x, then in average, this integer part is x minus 1/2. And our numbers g of m plus 1/4, it's can be in a sense considered as random numbers, and so this integer part is something like g of m minus 1/4. Well, I forgot to say that what I am telling you now, it's not the proof at all. It's only the some ideas why it must be valid. Well, and so if we consider this sum, which we have to consider integer part of g of m plus 1/4, then it asymptotically it will give us this this integral, which we remember is equal to lambda over 8. And if we believe to this calculation, then we have minus 1 over 4 for each term. So well, I'm sorry, I write here the answer not for this general theorem for arbitrary function little g, but for the case when this little g is g capital. So it's probably, it would be better if I write here. So by this hand waving, I want to say that we obtain here this integral lambda over 8 minus, and for each term in average we have this minus 1 over 4. So we have here minus square root of lambda over 4, and this is this corresponds to the second term in a Weyl law for the disk. Well, but we don't prove now, and we don't want to prove now Weyl law. We want to prove the Polya conjecture. And so if we have here this minus 1 over 4, it then we see that this number is lesser, strictly lesser than g of m, and so we hope that we prove this theorem 5 in its full generality. And now what about the rigorous proof of this theorem? We do the following way, the following thing. We take the once again graph of this function, and we divide it by a horizontal line at each integer point, 0, 1, 2, 3, and so on. And next we consider each such piece of our graph separately. So I want to say that this theorem 5 follows immediately from the corresponding claim for one such piece. So it's our K lemma here, the following lemma. Once again, let G be a decreasing convex function on the interval a, b. Once again, a and b be integer numbers. Once again, we assume that the derivative is in absolute value is not greater than 1/2, and we assume that all values of our functions lie between n and n plus 1, where n is an integer number. Then the following sum, 1/2 this construction for the left end of the interval AB, plus 1/2 this construction at the right end of the interval. By this construction, I mean integer part of the value of the function at the point at this point plus 1/4, and plus the same of such construction for all points inside the interval. And I want to say that this sum is always less or equal than integral from a to b of the function g. Well, if we prove this lemma, then theorem 5 follows immediately by summation of such things for where it is for all these pieces. And so we need only prove this lemma, and well, I don't want to give the rigorous proof. Once again, let me explain some idea why it must be true. let me show the following picture. We have this interval from n to n plus 1 in the interval in the values of our function. And there are here bad points. And there are also good points. By bad and good, I mean the following. If we have the point somewhere here, we want to calculate the value of this function, then add 1/4, we go up, and then we take an integer part. And then we obtain n. For all these green points, we have the value of this quantity g of m plus 1/4 integer part. It will be equal to n for this part of our graph. And for bad points are the points where the fractional part of the value of function g is greater than 3/4. Then we obtain n plus 1. Well, if in our picture there are no bad points, then the left-hand side of this inequality at each term is equal to n, and so we have n times b minus a, where b and a are ends of our interval. The right-hand side is always greater or equal than n times b minus a, because by assumption at the last point b, g of b is greater or equal than n. So this area is, this curve is always up than this line n, and so the n times b minus a, it's the area which is under this line, so we have it always. So if there are no bad points, then there are no problems. The left-hand side is clearly less or equal than right-hand side. But if we have some bad points, then the left assume that we have say k bad points. Then here we have we always have this number n times b minus a, and the first k points give us extra plus 1. So we have, but here we have 1/2, so we have k minus 1/2. So if there are k bad points, k is a natural number, then left-hand side is equal exactly n times b minus a plus k minus 1/2. And right-hand side is equal, once again, n times b minus 1, it's the area under this line, plus the area of this curvilinear triangle. And well, at this point is not, of course, rigorous, but the area of this curvilinear triangle is something like b minus a over 2. And b minus a is just, well, it's b minus a. It's the, well, we have triangle, we have with right angle, and we have one edge which is equal to b minus a, another is equal to 1, so it's something like b minus a over 2. And b minus a is just equal to number of all points minus 1. And next we use the convexity of our functions. And I want to say that it's clear from the graph that the number of good points is always greater or equal to the number of bad points, because our function is convex. And so the number of good points must be at least the same as the number of bad points. And therefore, the number of all points is at least 2 number of bad points. Number of bad points is denoted by k. So we have here at least 2k. And so we see once again that the right-hand side is greater or equal to the left-hand side. Well, of course, it's not the proof, but the proof goes as follows. We have to consider several cases. When k, the number of bit points, equal to 0, when k is equal to 1, when k is equal to 2, and when k is greater than 2. And that's all. And in each case, we obtain some simple inequalities which give us the result. Well, so if now you believe to this lemma, then once again, I repeat, by summation, we obtain the theorem 5 about this number of about the comparison of the number of integer point under the curve and the area under the curve, and with the explicit properties of the function g capital, and this estimate for Bessel zeros, we obtain the Polya conjecture for the disk in the plane. Well, if everything is clear now, let me say some words about our other results. The simplest result is for the circular sector. Here we have the sector in the plane. Here we have the angle alpha, and here also we have the separating of variables. And now instead of exponential, we have a sign of something, because we have to satisfy the Dirichlet conditions on the boundary. It must be 0 for phi equal to 0 and to phi equal to alpha. So we have sign of m times pi times phi over alpha. M is natural number. And once again, we have for the radial variable, we have Bessel function. Now with index m times pi over alpha. And therefore, corresponding eigenvalues are squared 0 g k squared of the Bessel eigenfunction with this index m times pi over alpha. And this time we also can write the explicit formula for accounting function of eigenvalues in this sector. It's the sum over m of the number of zeros of Bessel function with such indexes which are lesser than square root of lambda. And once again, by the inequality for the Bessel zeros, we can estimate the sum via the sum of integer part of the same function g capital, but at point this time not m, but m times pi over alpha. And once again plus 1 over 4, and once again integer part. And now we introduce the function little g of t, which is just dilation of the function g capital of pi t over alpha. And now we see the same, almost the same sum, g of m plus 1 over 4. And we know that it's lesser than the area under the curve, so it's the integral from 0 to alpha square root of lambda over pi in g of t dt. And we change a variable to in inverse direction, and we obtain here alpha times lambda over 8 pi, which is exactly the quantity which we have in the Polya conjecture. And I want to say that this case, the Dirichlet case for the sector, is simpler than the Dirichlet problem in the disk due to this, due to the boundary conditions. Here we have some which start from 1. In the, well, I'm sorry, probably it's not visible. In the case of the whole disk, we have here something about g of naught 1/2 plus 1/4, blah blah blah, and now we simply have known this term due to the boundary condition. So the case of the sector is, we can say that it's more simple. Well, and now what about the multidimensional situation? In a multidimensional situation, we consider only the ball, and I try to explain this only in 3D. Well, once again, we do separating of variables, of course, and we have that the formulas, explicit formula, a well-known explicit formula for eigenfunctions. It's the product of spherical harmonics, Ym, of theta. Theta is the point on the unit sphere, times 1 over square root of r, and times Bessel function, but this time it's not j with integer index, but this is Bessel function with integer plus 1/2 index, j of m plus 1/2. And the corresponding eigenvalues are squares of this, once again, zeros of Bessel functions, but not for the function jm, but the function jm plus 1/2. And for each natural m, everybody knows that the space of spherical harmonics in R3 has the dimension 2m plus 1. And therefore, these eigenvalues have the multiplicity, which increase with the number m. In two-dimensional case, the multiplicity is always 2, and now it's 2m plus 1. And so we need to do the following trick. The counting function itself is equal just to this sum. The number of roots of Bessel functions, which are not greater than square root of lambda, and the number of such roots has to be multiplied by 2m plus 1. And we sum this stuff from over m from 0 to infinity. I forgot to say everywhere that all this sum seems to be sums up to infinity, but it's very well known inequality that for any Bessel function j nu, even the first root is greater than index nu, and therefore all these sum are finite, because if this indexes m plus 1/2 is greater than square root of lambda, then there are no such zeros, and all these terms vanish. Well, so we have this sum. Once again, we use David Sher's inequality, and we obtain the following sum. Once again, integer part of something plus 1/4 times 2m plus 1. And we can rewrite this sum in the following, I say, triangle way. The first line is g 1/2. Well, let me, for now, I will not pronounce all this plus 1/4 and integer part. I will say only 1/2, 3/2, and so on. So in the first line, we have g 1/2, once plus 2 times g 3/2 plus 2 times g 5/2, and so on. The second line starts from 3/2, once then 2 times g of 5/2 plus 2 times g of 7/2, and so on. The third line, which is not here, written here, but it exists, it starts from 5½ plus twice 7½ and so on. And next, for each line, we can use our estimate for such sums. We know, it was theorem 5, I guess, that the first line is lesser or equal than 2 times integral of the function g capital of t dt, and the integral is over the interval from 1/2 up to square root of lambda. For the second line, we have the same integral of the function g, but here the integral starts from 3/2. The third line can be estimated by the third integral, which is not written here, which starts from 5/2, and so on. And in this way, we obtain here, let me write something. It's equal to 2 times integral from 0 to square root of lambda of some auxiliary function f times g capital. And this auxiliary function f is, is a piecewise constant function. Yeah, it's 0 up to 1/2. Next, it's 1 from 1/2 to 3/2. Next, it's 2 from 3/2 to 5/2, and so on. And this function is very similar to a linear function, which can be drawn here. And this is just the function t. And I want to say that this integral is can be estimated by 2 times integral of the product t times g of t, due to the fact that the function g is a decreasing function. It's very simple to see that this inequality is true. And finally, this integral of the product t times g of t, it's equal once again just to the principal term of Weyl asymptotics. And so in this long chain of inequalities, we obtained the proof for the Polya conjecture for the three-dimensional ball. The proof for the multidimensional ball is ideologically is the same. Well, and now if I guess I have several minutes. Do I have?
Yes, about 5 minutes.
Thanks. Then let me say some words about the Neumann problem, which is more complicated. And first, let us consider a two-dimensional case. And once again, let's consider the disk in 2D. We have again explicit formulas for the eigenfunctions, and the difference is here that here we have g prime. In UK, it's case 0 of the derivative of the Bessel function, and eigenvalues are these zeros of derivative of Bessel function squared. And so the counting function for the Neumann problem can be written in the similar way, but everywhere we have we have to calculate not zeros of Bessel function itself, but the zeros of its derivative. And for these numbers, we also have the estimate. And now from we want the estimate from below, and we have the estimate from below. The number of zeros of derivative of Bessel function, which are the number of zeros which are not greater than square root of lambda, is less is greater or equal than the same function g capital of nu plus this time 3/4 and once again integer part. And from this estimate, in the similar manner, we can prove the Polya conjecture for the disk and for circular sectors. And for circular sectors, it's more simple situation. Once again, due to the boundary conditions for the disk, it's more complicated. And let me try to say where is the problem. Now we have the same function g. Once again, we want to calculate some integer points, and we divide it by the graphs by some horizontal line. But now the good points are, now we want that this quantity will be large. We want to prove the Polya conjecture for the Neumann counting function, and this is the inequality in inverse direction. So we want that this quantity will be large, and so the good points when the fractional part of g of m is greater than 1/4, and bad points are the points where the fractional part is less than 1/4. So we divide this graph not by integer points, but by points 1/4, 5/4, 9/4, and so on. And for these parts of graphs, everything is okay. But now we have the last part of graphs where the values of these functions are between 0 and 1/4. And then this integer part of j of m plus 3/4 is just equal to 0. And so this part of graphs give something to the area under the graph, under the curve, but it make no contribution to the sum. And so it's some trouble, but we can deal with it. And finally, we prove the Polya conjecture for the disk. For sectors, the proof is also purely theoretical, but for the disk, unfortunately, it's is theoretical only for a large enough spectral parameter lambda. Lambda must be greater or equal to something like sorry, I don't remember, something about 170, and it doesn't matter because for lambda which are lesser than this number, it can be verified with computers very simple. Well, I think I stop here. Thank you very much.
Thanks a lot, Nikolay, for this talk. We are now ready for some questions. So if you have questions, you can just unmute yourself and ask them directly.
Okay, thank you. It's very interesting. I just want to make a historical note. You said that previously Polya conjecture was known only for tiling domains. In fact, Ari Laptev proved some time ago that Polya conjecture is valid for any domain that is a product of a domain for which a Polya conjecture is true and anything else. And these domains need not be tiling, for example, product of a tiling domain and anything else. And as far as I remember, back in the late 70s, Mikhailets proved Polya conjecture for cylinders. It means any domain cross an interval, the Cartesian product of a domain with an interval. Just historical remarks, but of course it's completely amazing. So, what do you think?
Leonid, thank you very much. We know, of course, about the Laptev result. I'm sorry to not mention it. Really, if you have two domains, for one of them you have the Polya conjecture, and the second is arbitrary, then you have the Polya conjecture for the product with the condition that the dimension of this first domain is at least 2.
Yeah.
But I don't know about this Mikhailov's result. If you could find some reference or something, it will be very interesting.
I will try. Just I remember there was a conference in 1978, and he was giving a talk, and I was at his talk. So I don't remember if there were proceedings of the conference. I definitely have them in my office. I will check tomorrow when they're going to be in my office. So.
Yeah, thank you very much.
Thanks, Lenny, for the question. Do we have other questions or comments for Nikolay?
There's a question in the chat.
Oh,
yes, I see. I'm sorry. What is? I'm sorry for the ignorance. What is the geodesic ball?
I think it would refer to any geodesic ball, but I don't think that you have your precise formulae for.
You mean ball in some
in a
manifold?
Yeah.
Well, I think no. I think well, definitely we cannot. But I think it will be not true in manifolds. But I don't know.
Mm-hmm. I mean, certainly for a large enough geodesic ball in a sphere, it would not be true.
It's not true.
Do we have other questions for Nikolay?
Suppose one further historical comment is that the existence of this, the relationship between the counting function of the unit disk and this function g, it's well understood that people have known before that the two are closely linked. This, I think, dates back to Kuznetsov and Fedosov in the 60s, as well as to Colin-de-Verdière in around 2010. The inequality is new, but the presence of g as a critical function for understanding this counting function asymptotics is not.
Yeah.
Just a historical comment.
Thank you. Thank you, David. I had a question of my own. So in the Neumann case in higher dimension, is it easy to explain what's the obstruction to obtaining the result?
Yeah. The first abstraction is this tail, which is rather difficult to deal with it. And the second is the following. Consider the ball in a multidimensional case. Then we have also explicitly the eigenfunctions, which are spherical harmonics times some Bessel times r to power 1 minus d half. And this time the eigenvalues squared are zeros of the derivative of this combination. If d equal to 2, then there are no this factor r to 1 minus d half is 0, so we have Bessel or Bessel prime derivative of a Bessel function, and there are many information about zeros of Bessel functions and its derivative in the special books. But if we consider the multidimensional case for Neumann, if we consider multidimensional case for Dirichlet, then we discuss the zeros of this product, which is just the same as the zeros of Bessel itself, because this thing is not zero. So also we use the information about the zeros of Bessel, which we already have and understand very well. But we have no information about the derivative of such product, and as far as I know, in the literature there are very little. But now we are working on it, on the multidimensional case. but for the, so it's the work in progress. But for the moment, we can say approximately nothing.
That's not exactly true. We can prove it with a gap for the time being. We can prove it that it's true above some lambda which increases in your notation as d's cube times some constant. And we can also prove it below some number which increases as d cube with some constant. But unfortunately, there is a gap in between constant. Constants also depend on d in a complicated manner, but bounded. So above and below, we can do it. In between, we can do it for any fixed dimension d with computer-assisted argument. And computer-assisted does not use numerics. It uses only integer arithmetic, so it's rigorous. But there is a gap which we hope to eliminate in the forthcoming work. So
I see. Thanks, Michael, for the precision.
So basically, there is a small gap.
All right. Do we have other questions and comments for the speaker? All right. Well, we will reconvene next week with a talk by Badreddin Ben Helal. Will talk to us about curvature contributions to the essential spectrum of Dirac operators with critical shell interactions. So we'll see you all next week, and thanks for being here, and thanks, Nikolay, for the talk.
Thank you very much.
Thank you.
Thank you.
Thank you.